Hello everyone. In this video, we're going to be doing a brief recap of the ANOVA design and looking at analyzing multi-group designs. We've talked about a lot of this in our courses, so this is really just going to be sort of the bullet point version of this, just as a resource for you all. So again, remember the whole purpose behind looking at these type of analyses comes with the extension of the designs we've been talking about. So now we're talking about extending designs to deal with more than one comparison at a time. And that allows several benefits, including being able to ask more detailed hypotheses and also reveal more nuances in your data. So you can actually get a better feel for what the influence of your independent variable actually is on the phenomenon that you're studying. So once we have done that and designed that, we really needed to find a way to analyze this. And this is one of the reasons why we didn't start to see these designs until really in the middle of the 20th century, because before then we didn't have this analysis, which is known as the analysis of variance, and take that literally, this is what it's doing. And the way to think about it, as we talk about, is that this is an extension of the t-test, that it's comparing differences between distributions to see whether or not the spread that we're seeing in these distributions or the distance between them is enough that we wouldn't see that kind of separation by chance. So we're asking the same type of question. The reason why the ANOVA was such a great advancement is for things that we talked about in class. One, it allows us to avoid making inflated type 1 errors by having to run multiple comparisons using a two-group analysis. So in the case that we had on the last slide, we're looking at 7 analyses at least on the same data to get all the comparisons that you would need. And that would inflate our error rate pretty substantially and increase the chance that we'd find something just because we ran multiple analyses, not because there's actually something there. The ANOVA helps us get around that, in that it does all those comparisons at one time. And again, this is what we talked about as being the biggest advantage to this. So talking about what it does, it is an omnibus test. That is, it's a scattershot analysis. It's going to look at everything, and it does so at once. So that's, again, the power of it. And one of the things that we have to be careful of when we're trying to interpret what the ANOVA is actually telling us. What it does tell us is that somewhere amongst all the comparisons that we made, there's a spread or a distance between two of the distributions that we're looking at that is far enough out that we would not expect it to happen by chance. So it does not tell you what specifically that difference is. And this is what we talk about this in class. The things to do are things like look at your data, plan ahead to do comparisons, to look at specific things. Or here's the thing, particularly for the grad students, you can actually forego the overall ANOVA and just do the planned comparisons as your main analysis too. And we'll talk about why that's an advantage. And then finally, you can also perform post-hoc tests, which are basically looking at those specific characteristics after you've run the ANOVA. Now, if you don't plan ahead, and I think I mentioned this in both classes, remember that you have to have a significant overall ANOVA in order to honestly look at these secondary analyses, because if the overall wasn't significant, then going back and looking at the comparisons, individual comparisons, is now running the same problem that we had with running multiple t-tests. That is, we're going to get false positives more likely than we would have otherwise. So let's take a look at it. What does this look like? So the key thing is that this analysis is all about variance. It's all about the way that things are moving around in your data, the spread that we're seeing in the data. And what it is really trying to do is account for what's producing that spread. That's essentially what the analysis is doing. So we went over this in class. The main tool it's using is something called the sum of squares, which is going to stand in for variance. And we talk about there's two forms of this, the computational formula and the definitional formula. Now, you can actually get one from the other, so that's okay. But the thing to get is that what this is the sum of every score subtracted from the grand mean. So we're looking for where does every score fall in relation to its mean. That's going to form a distribution. And then what we're trying to understand is what's creating that distribution. That's what the analysis does. So if you remember from early in the semester when we talked about the two primary types of variation we could have, systematic and unsystematic, well, the ANOVA, particularly for single factor ANOVAs like we're talking about today, categorizes this as between variance and within variance. So between, we refer to your systematic variance, that is the thing that you're producing, and within is the error, just things happening because they happen. So what it's doing, again pictorially, and you guys have seen this, is it takes this overall variability and tries to break it into components or sources. And your goal experimentally is that your between source should account for more variability than your error. And the way this picture is drawn is kind of equivalent. So this would be the null case. But we've talked about this. So we went through in class, how do we partition this? How do we break out these pieces from that? So mathematically, these slides just sort of walk us through there, where we're doing a little bit of math magic to remember, if we add and subtract something, we're not changing the nature of the equation. It's still the same equation. And then we can use that to help us break things into their sources. And then we're doing a little bit of factoring. Then here, moving the bracket gives us these terms here. These are our two terms here. This term's actually going to sum to 0. So what you're left with is that your total variability is equal to variability of groups from individual scores from their mean and from group means to the overall mean. So deviations within a group, deviations across groups. That's what this tells us. And that's the heart of the ANOVA. That's really what it's doing. And when you get to more complex designs, what you're able to do is break these things into more specific categories. All right, so we talk about the rules of thumb and a couple things with this. And again, these are kind of extreme cases, but just rules of thumb, one, to think about it in terms of math, and two, in terms of remember what this thing is doing. It's trying to account for where the variability is going. So again, if we noticed, if you have a sum of squares total that's equal to your error, that tells us there's no effect of the treatment. Again, this is an extreme example, but this can just tell you kind of how to weight things when you're looking at things, the numbers. If you have your sum square total equal to your sum squares between, that tells us that all the variability is being accounted for by your effect, and there's nothing left over for random variance. Now, again, these are extreme examples, not like they happen in real data, but I just want to sort of push that concept on you, that this is how these things kind of balance each other out. As we mentioned, the F statistic is a ratio, and it's the new terms we're introducing here are mean square and mean square between and mean square within. These are simply the sum of squares divided by their degrees of freedom, and that gives you the actual variance that we're comparing across the groups. So again, we're looking for how much can we account for by what we know and what we did versus how much is just there by chance. So we talked about this, the null case being that they contribute equally, or that your effect doesn't contribute more to understanding the variance than chance would. Typically, we want this to be greater than 1, and how much greater than 1 depends on several factors, including your sample size, the amount of error in your sample, and the magnitude of the effect. We talked about F being less than 1 as being typically attributed to being a sloppy experiment where you just didn't control things well. But there's also that other alternative where it could be because the manipulation itself is variance reducing. So it's a new thing just to think about. There's not really a way to address that within the analysis, but there is a research reason why this could happen besides just not doing research well. And then finally, we talked about that you can't have a negative F. And this simply goes back to the fact that everything that goes into analysis is squared. So it's impossible to have a negative square. So you know if you're seeing this either in your hand calculation or in your program, something has gone horribly wrong. All right, so then when we're talking about the logic of this, there's a couple of things. Again, this is just a pictorial, just kind of gives an idea of how we're partitioning things. So in a one factor where you're manipulating one thing, you're typically looking at stuff that is due to your treatment and stuff that's due to the error. And as we talked about before, this is going to have the most error relative to the other designs because we're not accounting for as much. So there's a lot of stuff that's going mixed in here. There's actually a lot of stuff that's being mixed in the between group as well that we haven't accounted for. So while this is a straightforward design, it has a lot of error relative to other designs, which means that your effect is going to have to be stronger. So again, just thinking about the consequences of how these things work. If we do it as a within design where we're using the same people, as we talked about, the advantage of that is we can remove the variability that's due to people being people. Because while we're different from each other, we're consistent within ourselves. So we can treat that consistency as a systematic variable and take that out. So what happens is when you're using within design, you can take out the variability that's due to people, and all you're dividing by now is not this total error, but just the error that's left over once you account for your effect and once you account for people being people. And this tends to be a whole lot smaller. So for the same size effect, you're much more likely to find significance because you're dividing by a smaller error term. That is, that your particular interest now accounts for more of what's going on. We could talk about this in the match as well. And the match has this kind of interesting hybrid function that it can be treated as a one factor if you're treating your match or your blocking variable as a control variable, or this could be a factorial design where you actually look at that explicitly to see what effect that has. So here again, what we're doing is we're partitioning, and what I want everyone to see is that the more we can account for, the less that's left over to deal with error that's just random around. So the short of all this is that the design matters. So that's just the overview conceptually for this. And what I want to leave you with before we take off is just thinking about what assumptions go into this design. So the first thing, as always, is this appropriate for the study you ran and the data you collected? Those are two separate questions. There's a time when people would try to do the ANOVA for everything and with all types of data. It is not appropriate for that. So you do want to make sure that your data is at least interval level. You want to make sure that your study has sort of groups that can be broken into categories. It's a categorical break rather than a continuous break that you would typically use for a regression. The other things are assumptions that come along with almost all parametric statistics. One, that your observations are independent. That is that they don't have any linear relationship with each other. If they are, there are corrections, but that's for another topic. Two, that the distributions themselves or the errors in terms form normally so that everything looks like a normal distribution. Now, again, this can be achieved simply by increasing your sample size, because once you increase it, everything tends to take a normal form, even if the original data was not. And then third, homogeneity, that the groups you're comparing have the same characteristics in terms of their shape and their spread. This typically gets violated when you have multiple groups that are different sample sizes. ANOVA is fairly robust with that, but it does make it difficult to equal out the distributions. And again, there are corrections for this. There are modifications that you can do that make the test a little bit more conservative. But these are the general things that most parametric stats look at or assume. And really the only one you have to be extremely careful of is the first one. Independence is a key thing. Normality, we can bend a little bit. Homogeneity, we can bend a little bit. Independence really plays havoc with these type of designs. All right, so that's going to do it for this overview. And the next part, we'll just talk about actually calculating this and walking through some of the analysis. So I will see you guys on the next round.